Yeah, yeah. You can see the screen.
Sir.
Okay. So this question which we saw last time. So is it clear now?
No, sir. Can you please explain it again?
Yesterday we saw, right? A toy car with charge Q moves on a frictionless horizontal surface under the influence of electric field. Okay. So once a charge is there in the electric field, the force on the charge is Q dE, right? This you know.
Yes, sir.
Okay, so velocity will increase because whenever force is there, acceleration is there, because force and acceleration are same, just that force is m into a. So just a factor of mass, force and acceleration are same. The velocity from 0 to
Yes,
6
sir.
seconds in 1 second at the instant. So at that instant, after 1 second, the direction of electric field is reversed. Okay, so the acceleration in the opposite direction. The car continues to move for 2 more seconds under the influence of this field. He's not saying anything further. It's so our region of interest is from 0 to 3 seconds. So average velocity, average speed. So if you draw the velocity versus time graph, 0 to 1 seconds, it will be a straight line like this. Velocity is 0 because starting from rest, as he said that. Okay.
Yes.
Okay, starting from rest, the electric field is switched on only at t equal to 0. And after 1 second, the direction of the acceleration will change. So velocity will keep on decreasing. And the slope of this and this will be same because force is same, right? Q into E, magnitude, only the direction is changing. So whatever is the positive slope here, that should be same the negative slope on this one. So it will go up. So the next 1 to 2 seconds it will become 0. That you are able to understand?
No, sir. On what basis you are saying that it will stop at the second? At
Because
velocity?
see, magnitude of acceleration and deceleration is same, right?
Oh, constant acceleration.
Yeah. Because electric field is uniform, right?
Yes, sir.
So the force is Q to E. So after 1 second it's minus Q to E. So whatever is the acceleration value, the magnitude is same for the deceleration also. So if it takes 1 second to increase from 0 to 6, it will take 1 second to decrease from 6 to 0. V equal to U plus AT. A is positive, U is 0. So the time taken is by final velocity by A, right?
Sir, but at second, the car must stop, no, sir. Because no velocity.
Velocity is 0, but acceleration is there, no?
Oh, okay.
Acceleration is the force. See, for the thing to stop, force has to be 0.
Okay.
Force is same as acceleration, except for the. So force is there on the negative direction. So first the force is trying to bring it to 0. After that, it's trying to return it. This thing. So if you draw a 1D picture, so 0 to 1 seconds, it's moving with velocity increasing.
Yes, sir.
After 1 second, up to 2 seconds, velocity is constantly decreasing. And after 2 seconds, it's turning back. It will come up to here. Got it?
Yes, sir.
So V versus T graph, this is the one. And why is it a straight line? What is the slope of a straight line? Constant, right?
Yes, sir.
It's a constant force. The acceleration is constant. So that is why it's a straight line.
The slope is constant. Okay. Yes, sir. The slope is acceleration.
Yeah. V versus T graph. So slope is acceleration. When force is constant, acceleration is constant. And similarly here also it's constant, but it's negative slope. So average velocity is integral v dt by full time duration. So this is a basic definition. Okay, so this you should know. Average of any quantity, you just have to take that quantity into a small time interval divided by the total time interval. That is the meaning of average.
Okay.
Even for a AC current, if you want to find the average current, I just have to take I into dt integral divided by the total time dt. This is a
Yes,
if you have discrete numbers, 3 numbers, I have to take the sum and divide by 3. Similarly, this thing I take small intervals, so add them, divide by the total interval. So integral VDT is the area under the curve. So V average means, and this area is positive, and this area is positive, and this area is negative. You know why this area is negative, right?
yes, sir. It is below the X
Yeah,
line.
it's integral V dt. So V is negative, dt is always positive. So V is negative. So it's area of this small rectangle. So area of all the rectangles is negative. Dt is always positive because we are taking the direction of increasing time. Here V is negative. So all the VDTs will be negative. So the full area will be negative. And this area and this area are equal because this base is 1. Here also 1. And in the same slope.
Yes,
So these two areas will cancel. So only this area will remain. So this area is half into base is 1 second. And how much is height?
6.
So half into base into height divided by the total time interval. See, average means I have to take the total time. So the time is from here to here. Because I have to find
Yes, sir.
average from 0 to 3 seconds. This area also I have to take the area from 0 to 3, but this area will cancel. So only this area will remain. So this area is this one divided by 3. So it is 1 meter per second. Is that clear?
Yes, sir.
So average of speed is integral the magnitude of the velocity. I don't have to bother the sign. So this will look as if it's like this only.
Yes, sir.
So all areas will become positive. So it will be thrice the area of this triangle. That is half and base with height into 3 times. So it will become thrice of this one. So it's 3. So correct option is option 2.
Yes, sir.
Okay. So the important, okay, for first thing you have to remember is this formula. So once you remember this formula, you know it's something related to the area. If you have the VT graph. So just see whether we can get the VT graph of this problem. So it's a uniform acceleration. So VT graph will be a straight line. This acceleration is constant. Okay, you have after I do the class, you revise it one more time tomorrow or something, so that you'll remember. First, try to do the question without looking at the solution, and then if you don't get it, you look at the solution. And this one,
No, sir. I can't
see,
understand this one.
see, whenever an object is neutral, okay, even if you take a single atom, it is neutral, right?
Yes, sir.
Nucleus is positive, the electrons are negative. So if the atom is not ionized, it's neutral. Okay, so even if I take a single atom and apply an electric field to it, slightly there will be a separation of positive and negative charge. That's a similar thing I was studied in dielectrics, no? Polarization of dielectric.
I forgot that concept,
Okay,
sir.
usually this is the say atom. So in the center it will be positive and surrounding there will be electrons, right?
Yes, sir.
Okay, so if you take as a whole, if there is no electric field, it will be both center of the positive and center of negative will coincide. You can assume, see the center of this, you can assume that the electrons are in this spherical shell. The center of negative is also here, no? Got it?
Sorry, sir.
No, you take a simple picture. Say the electrons are symmetrically distributed, right?
Yes, sir.
So if you look from far away place, okay, it will look at, instead of this having a shell of electrons, I can concentrate the whole. What is the center of this electron distribution? This center point, right?
Yes, sir.
Okay, so in some sense, the center of the positive distribution and the center of the negative distribution coincide. Okay. because center of a spherical shell is the center, right? And nucleus is also at the center.
Yes, sir.
Okay, so the center of the positive charge, that is the nucleus, and the center of the negative charges, which are the electrons which are distributed around it, both of them coincide. Okay, but when you
For the persons, but only with the.
See, if you have.
That is assumption only.
Yeah, no, it's valid. No, so just take a 2D thing. Say this is the circle. I have one electron here and one electron here. What is the center of this negative distribution?
Nucleus.
Center point, right?
Huh.
So even if I have 3 electrons separated by 120 degrees. Okay, not like this. This is actually 90. So if you have 4 electrons here separated by 90 degrees, what is the center of this electron distribution? This
center point.
So in general, for an atom which is neutral, both positive center and negative center will coincide. But once I apply an electric field, say in this direction, this positive this thing will experience a force in this direction, right?
Yes, sir.
And the negative this thing will experience a force in this direction.
Yes, sir. Opposite direction.
Yeah. So once I apply this electric field, it will be slightly separated. Positive will be here and negative will be here. Previously, both positive and negative are sitting on top of each other when electric field is 0. Once I apply the electric field, there will be some small separation. Okay. So this is equivalent to minus Q plus Q, and this is dipole. So when there is no electric field, it's as if the whole thing is not charged. But once I apply an electric field, there will be a small separation between the positive center and negative center. So this I can equivalent to your dipole. Okay. So here we have a neutral water molecule initially, and once I apply the electric field, there will be a dipole formation. Okay. So the work done to rotate this dipole by 180 degrees is this one. So work done is increase in gravitational potential energy. Here the potential is electrical potential energy or electrostatic potential energy. And for a dipole in an external electric field, the potential is minus P dot E. That formula we have, no?
Yes, sir.
Electric potential of a dipole in electric field is minus P dot E.
Yes, sir.
So work done is increase in potential energy. It's basically work energy theorem, or you can say conservation of energy also. So work done is increase in potential energy. Work done on the system. So potential energy increases minus P dot E. So the change of that, and P dot E is P into cos theta. So I'm taking rotating by 180 degrees. So initially let it be at 0 degrees, and after I'm rotating by 180, so it will become like this.
Yes.
So one time it will be cos 0, another time will be cos 180. So I will subtract them. So 1 minus minus 1, so it will be 2. And P is Q into the separation 2A electric field, and work done value is given 2.5 into 10 to minus 25, and electron charge is 1.6 into 10 to minus 19, and electric field value is given. So 1.25 into 2 will cancel with 2.5, and the minus 19 plus 4, so it will become minus 10. This is
yes,
correct? Minus 2, is it correct? It's correct. No, it's minus 6, and then what done? 1.25 into 10 to 4.
Yes, sir. Correct only.
Right. This is becoming minus 15, right? So it's minus 10 only. After that, it will become 1 by 1.6, right? 1 by 1.6 is same as 10 by 16.
Yes, sir.
10 by 16 is 5 by 8, right? And 10 by 16 is 5 by 8. 2, you have to cancel 2, right? 2 times 5 and 2 times 8. And 5 by 8 is
Yes, sir.
0.625. This you can get it.
Yes, sir.
So 0.625
Correct.
10 raised to minus 10. No.
Option 4.
Okay. So,
Okay, sir.
so in general, atom will be neutral. So positive center and negative center will coincide. So when you put it in the external electric field, there will be slight displacement and behave like a dipole.
Okay, sir.
Okay. I think, okay. So this is over. Okay. So today we'll move the next chapter, that is capacitance and potential. What is electric potential, electrostatic potential, and why is it called static? Electrostatic.
The charges are not moving here.
Okay, because that's the simplest thing. We'll first do the simple thing and then we'll try to complicate it. So, what is electrostatic potential? You all should be knowing, right?
Integral of E dot ds.
Okay, that's mathematics. It's okay, fine. Let me get to it. So, work done on a body against a force moving from point A to point B, the potential will increase. This is clear. Whenever you do work on a body, its potentiality will increase. When a body does work,
Yes, sir.
it will lose energy. So potentiality will decrease. So work done is independent of path for a conservative force. This also, you know, an example of conservative force is gravity. And so in a gravity, say this is Earth, and say this is height. So if I have a ball here, and I try to move this ball very straight up to this height, and another ball here for the same ball, I try to move like this and move like this. So the work done in two cases will be same. You know this one? Because the work done from moving from here to here, that is 0. Okay, and similarly the work done, if I move in this direction, that's also same as the work done in moving in this direction. That is the property of conservative force.
Yes.
Uh,
Then what are the examples of non-conservative force, sir?
Non-conservative force in the sense friction. Suppose this is Earth's surface and I have a mass like this, and I'm trying to move from point A to point B. But suppose I, okay, let me assume it's point A to point B. I'm moving like this, and there is friction. Another path I'm moving like this. Again, the path is which has got friction. So this energy spent on this path will be more, right? Because path length is more.
Friction depends on path length as well.
No, friction force is independent of path, but the work done against friction is dependent on path length. If the path length is more, then the work done should be. Suppose this point is A, this point is B. I'm taking a car from here to here, and another path is this one. So on which path the fuel is spent is more?
A, that is curved path.
Curved path. So and car is doing work against friction. Suppose you assume other things are not there, wind and all is not there. So car is basically spending energy against the friction. So that is one thing. Even if you take a block, a wooden block on a floor, say, if you move the shortest path, the work done is less. So this is an example of non-conservative force. I'm moving from the same point A to B along two paths. The work done is more if the path length is more.
Okay.
Okay. Here I made a little bit mistake here. So one path is from straight path from here to here. Another path is say I move like this and move like this. In the case of gravity, the work done along these two paths are same.
Okay.
Okay, so conservative force, example of conservative is gravity, spring force. Coulomb force, electrostatic force is also a conservative force. Even the gravity force is also a conservative force. Okay, here I have two, here I have a positive charge capital Q and a small charge Q. So if you have to bring charge Q is at origin, so if you have to move this charge Q from this point R to P, do you have to work? Do you have to do work on this charge, or it will move on its own?
We have to do work.
Okay, the assumption you are making is both are like charges. Okay, Q is positive and this Q is also positive. I think that's being mentioned here. It's written on that charge. Both are positive, so I have to do the work. If it is negative charge, I don't have to do the work. Okay.
Yes.
So
Yes,
and
sir.
this work done is F dot dr. This is the basic formula. Okay. So this is the external force I'm applying on this charge. That should be opposite to the, that value should be equal to the electrostatic repulsion, and the direction will be opposite. Electrostatic repulsion will be in this direction. And the force I'm applying to overcome this one will be in opposite direction. Okay, so the work done is the external force I'm applying, that is minus the electrostatic force. So this work done is going in increasing the electrostatic potential energy. So increase, so it's the final potential minus initial potential energy. Final potential is UP. So UP minus UR is this one. Okay. So electrostatic potential is work done per unit positive charge. So this work done, UB minus UR, will be more if this value of Q is more. Because why will it be more if Q is more?
Sorry, sir, I don't get it.
See, this work done in moving Q from R to P will be more if the charge value Q is more. Yes? See, if Q is 1 coulomb, okay, then some amount of work is done from here to here. If Q is 2 coulomb, what will be the work done to go from here to here?
Twice.
Twice. So basically the work done is dependent on this thing. So one way to say that the repulsive force will increase. So I have to do more work. Okay. And so work done is proportional to the amount of charge. So electrostatic potential is defined as the work done for bringing unit positive charge. So instead of bringing charge Q, I'll just bring 1 coulomb, where Q is 1 coulomb from here to here. In that case, whatever is the work done, that I'll call as potential or potential difference between the points P and R. So whatever is the work done divided by the charge Q is potential difference between the points B and D. Is this clear?
Yes, sir.
So electrostatic potential at a point, this is potential difference, but it just have to define electrostatic potential at a particular point, say P. That is work done from moving the unit positive charge from infinity to that point. What is potential at infinity?
0.
Because its electric field is 0, and also I have to move the charge from infinity to infinity. So work done is 0. So electrostatic potential at a particular point P is work done from moving from infinity to this one. So it will be UP divided by Q. Okay, potential due to a point charge. So there is a source charge, say capital Q, and I have to find potential at this point PR. So by definition, I have to take a unit positive charge at infinity, 1 coulomb, and find the work done in moving this charge from infinity to this point. Okay, so we're going to move positive from at P prime by distance delta R. Okay. Suppose I'm moving from distance from here to here by amount delta. So it's work done is the electrostatic force, that is, this is the Coulomb force, kq by r square. Is this clear? Why is this force this one? because the second charge is 1. Coulomb's law is K into potential of the charges by distance square, right? So potential is your
Yes, sir.
unit positive charge. So the second charge is 1. So the force is K into Q by R square. R is the distance between the point and this one. So into the distance, that is delta, it's infinitesimal. So integral sign is not there. So work done in bringing positive charge from infinity to that point is we have to integrate this one. Instead of delta, we have to put dr. And this integral r raised to the power minus 2. So it will become r raised to the power minus 1. And you have to put the limits. 1 by infinity is 0. So it will become kq by r. So the potential at point P is kq by r. So this is the formula you have to know. Potential due to a point charge at the origin at a distance r is kq by r, where k is 1 by 4 epsilon naught. Electric field is kq by r square. Potential is kq by r. Okay.
Yes, sir.
If you differentiate 1 by r, you will get minus 1 by r square. Okay, and you have to take the negative gradient. Potentially, electric field is negative gradient of potential. So that negative will cancel with minus, so it will become kq by r square. Okay, so the formula of electric field you get from this one by differentiating, and then you have to put the negative sign because it's minus dv by dr. So 1 by r differential is 1 minus 1 by r square. So that minus will cancel with minus. So getting it, no?
Yes, sir.
Okay. So this is potential due to a single point charge that we got from basic definition as work done in moving from this one. Suppose I have a dipole, there are two charges. So I don't have to take the original definition of work done for. So I just have to say potential at this point due to this positive Q and potential due to this at this point due to the negative Q. So potential at point P due to a dipole is potential due to the plus Q and minus Q. And potential due to plus Q is K into Q by R. And for negative Q, it's minus Q by R2 because the distance is different. One is R1 and one is R2, right? This step is clear.
Yes, sir.
This potential at point P due to a dipole, and by using superposition principle, we can get this one. And R1 is related to R. Actually, if this thing is very, very small, or the point is P is very, very small, very, very far away, R is approximately equal to R1, and R2 is also approximately equal to R, the middle one. But in general, you have to write the general expression. So this formula, it's called cosine rule of a triangle. In case of right angle triangle, theta is 90. So it will become R square plus E square. In that case, this angle will become 90 degrees. And R is becoming hypotenuse. So this is becoming 90. Okay. But in general, there is some angle theta. Oh, theta is becoming 90. R1 square is, R1 is actually more, right? So yeah, I made a mistake. So this is 90 degrees. R1 is hypotenuse, that will be more. And this theta, in the case of right angle triangle, will become 90. So this term will disappear. So that's one way of remembering this formula. So it's R square plus A square plus a correction, that is minus 2A cos theta. And in this second triangle, this angle is 180 minus theta, right? So cos 180 minus theta is minus cos theta. So R2 square is this one. Is that clear?
Yes,
This is cosine rule. Okay, we will have minus sign, but in the second triangle, the angle is 180 minus theta, and cos 180 minus theta is minus cos theta. So that minus will cancel this minus and become plus. So from figure also you can see R2 should be more than R1. Okay, because R2 is more inclined. That's what is happening. R2 is plus and R1 is minus. So this dipole, the approximation is A is very, very small compared to this distance. So R1 square I can write like this, that you can take R square outside. Is this clear? This step. Okay. And once I make that approximation, this term I can neglect because A is very, very small compared to R. So E square is smaller compared to E. This is the approximation. Okay. Similarly, R2 square, this term I can neglect, and only difference is the plus will be here, there will be minus. Okay, the same approximation. And what it is 1 by R1, because in the formula it's 1 by R1. So 1 by R1 is, I will take square root of, so it will become 1 by R into square root of this raised to the power minus half. So this raised to the power minus half. So this step is clear.
Yes, sir.
Okay, and since A is small, this term is small, so I can use the binomial approximation. So this half will come here, and this minus will cancel this minus, and 2 will cancel this 2, so it will become this one.
Yes, sir.
Okay, so similarly,
So
1
that
by
binomial theorem is valued on rule is there, no, so that condition. That condition is what, sir? I forgot that one.
see, dipole means this A is always small. Dipole means the charges are separated by a very small distance. So this approximation is always valid, and it's also valid when this P is very far away. The same thing I talk about the water molecule, right? Or the in the previous form, positive center and negative center are separated by a very small distance. So usually in a dipole, their approximation is valid. E is very small.
Yes, sir.
Okay, so 1 by R2 will become this one, and this minus will come here, so it will become minus here. Okay, and V is 1 by 4% Q by R1. So Q I can take outside commonly. So Q will come out. So it's 1 by R1 minus 1 by R2. So I have to subtract these two. So this 1 will disappear, and this will come as twice. Is that clear?
Yes, sir.
Okay, so on Q,
2A cos theta.
yeah, and 2 will combine with 2A will combine with Q to become P. P is Q the charge separation. Charge separation is 2A because origin from origin this is at A and this is as minus A. So the total separation is 2A. So Q separation is the dipole moment P. And P cos theta is angle between P and R vector. P is from minus Q to plus Q. So this is P vector or P cap, and this is R cap. So angle between P and R is cos theta. So P cos theta I can write as P dot R cap because it's P into unit vector into cos theta. Magnitude of unit vector is 1, so it's just P cos theta. This is clear? So this is the formula you have to
Yes, sir.
remember, and this approximation we have used. Otherwise, this is not valid. It's true only for only this approximation is valid. It's usually valid for a dipole. So for a point charge is 1 by 4% of the charge divided by the distance. Here it is P dot R cap divided by the distance square. This P has got a distance dimension. It's Q to the distance. So that distance will cancel the distance and become Q by R. So dimensionally it is correct. So this formula you have to remember. So whatever I highlighted in green, they are all formulas which you have to remember. There is no option for that. You have to remember all these green boxes. They are formulas. So electric field at a general point is this. I'll go. This is not for. It's not in. It's not there in NCERT. So I'll just tell the idea. So to get the potential is gradient, right? So it's P into R into cos theta, and so okay. So potential. So basically, the electric field you have two components. One is gradient with respect to R, another gradient with respect to theta. So if we take these two derivatives, I'll get the electric field values of this one. But this is not there in NCERT. Okay, so we can skip. But this is a basic idea. So this V, if you look at this formula, okay, it has got two variables, right? One is R, one is theta. Okay, so
Yes,
when I take this space gradient, I can take either with respect to R or with respect to theta. Okay, so if you take the derivative with respect to R with a negative sign, I'll get the electric field in the direction of R. If I take the derivative with respect to theta with a negative sign, I'll get derivative electric field along the theta cap direction. Since we have to match the dimensions, I put R here. But this you can leave it. Okay. Fine. The electric potential in a region is given by this one. So it's a 1D problem because it's only one space dimension. Dipole is placed in the position 1, 0. Okay, here y-axis is coming with the dipole moment P pointing in the positive y direction. So here the second dimension is coming. Then the net force on the dipole is 0. Net torque on dipole is 0. Net, okay. Basically, you have to see whether torque is there and force is there. So, so is the electric field uniform?
No, sir.
Why is it not uniform?
Variable present. If we partially differentiate with that.
Yeah. So
Yes.
electric field will be function of x, right?
Yes, sir.
So this is the electric field. When it is, so electric field is this one, right? So this is so net force will not be 0. Net force will be 0. Okay. Another thing is the dipole is in the position minus. Okay. We have to see also how the dipole is placed. So the dipole is placed at minus. This is the origin. Okay. This is x equal to -1. Okay, and the dipole is dipole moment is in this y direction. So minus is here and plus is here. So this is the dipole direction. So in this direction, the value of x is same, right? For plus q and minus q. So electric field is same for this and this. So for this particular orientation of the dipole, the net force is 0.
Yes, sir.
Because x is same, but torque is always there, even if it is torque is not 0. So and the torque will be in this direction. Okay.
Sir, but P vector and electric field direction is I kappa, sir. Okay, 90 degrees from maximum.
See, you don't have to take a P vector at all. For the force, you have to take individual charges. Plus Q, the force is F. Minus Q, the force is also F. But the electric field value is same, right? Because X is same for plus and minus Q. This is X-axis, right?
Yes, sir.
And the dipole, the orientation is plus Y. So for this particular orientation, these two forces are same because X is same for both of them. In that case, the net force is 0. Suppose in the problem they have given, so the dipole is kept for 45 degrees like this. Suppose I mentioned like this, minus Q will be here, plus Q will be here. In this case, net force won't be 0. Here the force will be this much, but here the force will be less. As shown by shorter arrow. So in this, if this is the orientation of the dipole, then the net force is not 0. But the torque will still be clockwise.
Anti-clockwise, no, sir.
No. This force about this origin will produce a clockwise torque, no? This is the force. And it's going to rotate up about this point. If you have a rod like this, and I apply a force here, how will it rotate? About this point? Clockwise, no? Yes?
Yes, sir.
So, but the same force, if I apply it here, it will rotate on anti-clockwise. Okay?
Yes, sir.
It depends on the pivot also. It's going to rotate about the center point only because two charges will have same mass. Okay, so it's about the center of mass. So center of mass is below. So this force will try to rotate on the clockwise direction.
Yes, sir.
Okay, so but if the initial dipole orientation is 45 degrees, then the net force won't be 0. Even the torque will be clockwise.
Yes, sir.
Okay, so net force is 0 for this 90 degrees situation. So the correct option is it's multiple option A, and then net torque is clockwise. So A and C is the correct answers. Multiple option. Okay, for this orange one, net force, this is not true. If it is orange, net torque is clockwise. Okay, if the orange one is the initial condition, then the correct option C is C only. Is that clear?
Yes, sir.
Okay. The arrangement shows 3 elements. Can you see the 3 elements? 1, 2, and then 3. So thin rod of charge -3 microcoulomb forms a full circle. So first part is the full circle. It's a ring sort of a thing. Second is a thin rod, but it's a circular arc. It's a part of a circular arc. This one, and then of radius 4 centimeters. So this distance is 4. This is 4. And how much is this distance? How much is this one?
6.
6.
6.
Okay. And this thing, it's quarter of a. So this angle is 90 degrees. This angle is 90. And the third one is a dipole. These two is one is and perpendicular electric dipole that is perpendicular to radial line and has magnitude 1 point. Okay, here's one to which is positive and which is negative. Okay, net potential in volts at the center. So what is the potential at this center point? Can you get the answer? So we can do by superposition principle. So potential at the center is V1 plus V2 plus V3. V1 is due to the element 1, V2 plus V3, and what is let's do the simple one. Okay. Okay, what is
This is not a point, sir.
so this is K into Q1 by what is the distance in the for the first one? All the elements are same distance, right? 6 centimeter. And Q1, see if for the first one, if I take an element here and an element here, the potential of these two elements are same or different?
Same potential.
Same potential, and potential is a scalar quantity. Yeah, so just sort of add them. So if you add all these things, it will become Q1 divided by the total by the distance. So all the elements are at 6 centimeter. So the total potential is Q1, given the total charge of the element 1 by 6 centimeters. And how much is V2? It's
Sorry, sir.
V2 is potential to the arc.
Yes, sir.
So K into Q2 divided by what is the distance?
4 centimeters.
And what about V3? This distance, right? And both these distances are same. And one will be Q by the distance. Okay. One is Q by L, another one is minus Q by L. So these two will cancel. So dipole will not give any potential.
Sure.
Both plus Q and minus Q are the same distance. So it is K into Q by R, right? So plus Q will cancel this minus. So V3 will be 0. Is that clear?
Yes, sir.
So this is K into Q1 is -3 and Q2 is 2 by 4.
So it is like a potential due to rings is also equal to that of the potential due to point charge, sir. If the charge is
No.
magnitude of
No. See, this element dq and this element dq, the potential due to the element dq is dr, right? dq by r. You have to sum all the dq's, and r is same. So 1 by r will come out. So it will become summation of dq's. That is 2 by r.
okay.
Okay. Similarly, for this r, the potential due to the element here and the potential due to the element here, they are same. So we do this summation, I'll get the total charge of this arc. That is Q2. So all the elements of Q2 are the same distance. So it's just the whole Q2 by the distance.
If the point is not center means then we have to do integration only, no sir. For
Point
R
is
will be
center,
variable.
it will be complicated. That will be very difficult.
Yes sir.
Okay, so they will not ask that sort of question. Here the integration is trivial. Integration is there, but it's a trivial integration.
Yes sir.
Okay, similarly
The R is
huh?
if the R is variable means then it will be more complicated.
Yeah.
Right.
It's not possible here. Suppose instead of center point, we say you find potential at this point. Okay,
Like
then it's difficult.
Okay.
It's actually impossible.
Yes sir.
Okay, so this is the answer. You just have to simplify it, you'll get the answer. You have to put proper units. It's microcoulombs, we have 10 raised to 6, and then it's centimeters, we have 10 raised to -2. So if you put all those numbers properly, you'll get the answer. Okay, now we have considered point charge and the two charges, right? And that's a dipole. So instead of that, we can have more than two charges. Here you have system. So how many charges are here? 1, 2, 3, 4, 5. In general, there can be n charges. So here also we can apply superposition principle to get potential at any point. Where is the point? This is the point P. So that is K into Q by R. So it's K into Q by R1, Q2 by R2. So this is clear. So the potential at point P is summation of individual charges. Is this clear? And the corresponding distance.
Yes sir.
Okay. So now we have a spherical shell. Okay, we have to find the potential at the points outside. Okay, so see, electric field is we can consider as a basic thing. From that we can derive the potential. Okay, so the electric field of for outside points, electric field of a spherical shell is equivalent to so the spherical shell is equal to a point charge located at the center. This is the thing at for R greater than capital R. So this equivalence is valid for R greater than capital R. So it's as if the point charge is there. So the potential at this location is same as that of point charge. So it's K into instead of this Q, I represent as capital Q. So the force charge at the cell is capital Q. The potential at this point is KQ by R. So this is valid only for R greater than R. For outside of the spherical shells, because for outside the electric field is same as that of a point charge. So whatever electric field is there outside of the spherical shell, that is same even if the point charge is there. So when work done is moving the point charge, unit charge from infinity to this one, right? Since the electric field is same, the work done in moving for the spherical shell case and also for the point charge case will be same for R greater than capital, that is for the points outside of the shell. Okay, we are getting by a simple argument. Is it clear? And for the
Sir, can you draw that formula like a graph, sir?
no, right now graph is not required. We can get the graph later. Okay, but you understood that this expression, no expression of potential. See, if you have a point charge, what is the potential at distance r? K into Q by R, right? This is your point charge, and what I'm saying is the electric field pattern for a point charge and the spherical shell are exactly same. That we studied in the previous lesson, no? And while studying Gauss's law, the electric field outside of a spherical shell is equivalent to a point charge located in the center for points outside of the shell. So since the electric field is same, potential will be same, because when the electric field is same, the work done in moving the charge from infinity to that point is same. Because basically integral E dot dr. So since E is same, integration will be same. The value will be same. So for R greater than, for outside points, it's as if it's a point charge. So potential between point charge and distance R is this one. This one.
Yes, sir.
But for inside, inside for of a spherical sheet, the electric field is 0. This we already studied. So whatever is the work done in moving the unit charge from infinity to this point, after reaching this surface, you don't have to do any other work because electric field is 0. Work done after
Yes.
inside is 0. Once we reach the surface, to move further inside, electric field is 0 means there is no force on the charge. So work done for moving inside is 0. So whatever is the work done up to this surface, that is Q by capital R, that is the potential at this point, and whatever is the potential at capital R, that is the same potential at any point inside. So everywhere inside, the potential will be VR only. It will not change.
Yes, sir.
Because the work done in moving from here to here is 0. So since the work done moving from here to here is 0, the potential difference between these 2 points is 0. So whatever potential is here is same potential here also. So for all the points inside, the potential is constant or uniform, and the value is Q by capital R.
Yes, sir.
Okay, so you know this formula for point charge. So using that point charge, you can get up to the surface. And once you reach the surface, we know inside electric field is 0, so the potential will not change. So it will be whatever is there on the surface. So at the surface, we have to put capital R. So this formula you have to remember, and you can remember if you remember what is there for a point charge. And this idea of electric field outside of a spherical shell is outside of a point charge, inside it is 0. So this is the graph. 1 by R variation will inside will be constant. Okay.
Sir, can you please explain once again why inside the potential will be constant? Won't it be 0?
It is 0. See, potential is so moving from the surface to any point inside, the work done is how much?
0.
Because electric field is 0. Because work done is the unit charge into the electric field. So and the potential difference between these 2 points, V inside minus VR, equal to work done, right?
Potential difference is there, sir, but inside that one, potential is not there, no, sir.
Yeah. See, potential is what work done in moving a unit charge from one point to another point. The potential difference.
From infinity to that.
No. Infinity to 1, that point is the potential of that point. If you have to get, say, potential difference between point A and point B, okay, I have to move a unit charge from here to here. I have to move 1 coulomb from this point to this point. So whatever is the work done, that is equal to the final potential minus the initial potential. I'm assuming I'm doing work, so the work that is done will go in increasing the potential. So final potential minus initial potential. If the work done is 0, then the potential should be same.
But that graph we view not for potential difference, no, sir. We view for potential only, no.
Yeah, potential at any arbitrary point. So instead of
And then potential inside that one, then it should be 0 only, no.
no, potential will be uniform. Potential difference is 0. See, this VB is VR and V is V capital R. Okay, so V at R should be same as V at capital R. Electric field is gradient of potential, no? So if potential is uniform, means gradient electric field will be 0. E is 0 means the slope is 0. So slope of this potential is 0. So whatever is the potential here, it will remain throughout the same. So electric field is dV by dr.
So potential 0 means then it will not be present, no.
Potential is not 0. Potential has some value here, no?
Inside that one, sir.
Inside,
Below R.
inside electric field is 0. Potential is not 0.
And that's what I'm asking. Mathematically, E dot ds means E0 means and potential will also be 0, no?
Why V is 0?
E0, no, sir.
E is what? dV by dr, no?
Then you only wrote that E equal to 0, no, sir.
Hold on.
Inside that one,
Hold on. This is correct or not?
yes, sir. Dhoni by the
So
wall.
E0 means what? This slope is 0, no?
Okay.
So like V versus T graph, this thing straight line means acceleration is 0, right? That does not
Yes, sir.
mean V is 0.
Okay.
Okay, so similarly here, potential is uniform. So gradient is not, so electric field is 0. Because I've already chosen the potential infinity as 0. So once I fix this thing, I cannot choose potential the center point as 0. I can fix potential. I can fix potential at only one point, and after that I have to use that as a base and get potential at other points. I've already chosen the infinity and the potential is 0. So whatever is coming, this value, that I have to keep it constant.
Yes, sir. Got it.
Okay, and okay, and equipotential surface, what does it mean? Equipotential surface?
All the points on that surface will have same potential.
Yeah. So in electric field, we draw the electric field lines, no? Okay, and for a point charge, we show electric lines as readily moving outward, but actually that picture is drawn as a 2D. In general, in reality, it will be 3D. Okay, it's as if from a center point, all the lines are going out in all directions. Okay, so for a point charge, all the electric field lines will be, okay, that is one way of thinking about it. Another thing is, potential is 1/4 pi epsilon q by r, right, for a point charge, and it's depending only on r. And for all these points on the spherical shell, okay, it's not a circle, it's not a ring, it's a shell, spherical shell. You can visualize that.
Yes, sir.
Okay, so all the points on the shell will be the same distance from this point charge. So all the points on this shell will have the same potential, whatever is the radius. So the spherical surface is an equipotential surface.
Yes, sir.
Okay, so instead of a point charge, even if I have this spherical shell, in this case also, the equipotential surface will be a spherical surface.
Yes, sir.
Even this Gaussian surface is actually a spherical surface. So even in this case also, for the points outside, it's an equipotential surface. Even to the point inside is also equipotential surface, but there won't be any gradient.
Yes, sir.
So another thing is, what are the distance between two consecutive surfaces? Is it uniform or is changing?
Changing.
So when you draw the equipotential surface, you'll fix like, I'll draw one equipotential surface over 2 volts, second surface at 2.1, third surface at 2.2, 2.3. I have to fix the interval as uniform. So for the same uniform interval, the distance that's required to travel as you go out will be more. Okay, because the variation is 1 by r. For 1 by r variation, which is here, suppose I have to get a difference of 1 volt at this point, and I have to get a difference of 1 volt at this point. The corresponding r variation will be large here. Got it, no? Is it clear?
Yes, sir.
But if you have a straight line, it's uniform. There is a property of a straight line because related to the slope. This is straight line. For same delta y, the delta x will be same everywhere. That is the property of a straight line. It's only true for a straight line. It's basically related to the fact that the slope is same for a straight line. But here the slope is more at this point. Here the slope is more, and here the slope is decreasing. When the slope is decreasing with the same y, you have to travel a larger distance of delta x. In this case, the y is delta v and x is delta r. And while drawing equipotential surface, I have to maintain the delta v. Delta v is constant. So to get the same delta v at a larger distance, I have to travel larger r. So the distance between the spherical surfaces are increasing. Okay, and suppose I have a uniform electric field like the one which is there in between two capacitor plates. Here, the equipotential surface will be a plain rectangular sheet. Okay, because the potential at any point on this place will be same. Because the potential at this point is, suppose I take this point as a reference, the work done from moving from here to here. That is same as the work done from moving from here to here. So the potential at all the points will be same. Okay, so but the potential will not be, potential from this to this will not be same. Suppose this is the, say, capacitor plate, and this is positive plate and this is negative plate. Suppose this is plus 5 volts, this will be minus 5 volts. So in between, or we can say this is 0 volts. So it's 5, 4.9, or we can say 5 here, 4.5 here, and this is 0 volts. Okay, but all the points on this rectangular plane, the potential will be 4.5. Here all the points will be 5. Here all the points in the rectangular plane will be 0. But there will be variation from here to here, here to here, here to here, here to here. Okay, here will be 5, 4.9, 4.8, like that 4.5, 4.4, 4.3, finally will be 0. Okay.
So that distance varies, no, sir, for that.
No, for this thing it will not vary. It will not vary because E is uniform. Okay, E is uniform means E equal to dV by dl, right? So gradient is 0.
Then potential is 0.
No.
Sorry.
E is dV by dl. If V is uniform, there is no gradient. We can have same value 5, 5, 5 everywhere. Sorry.
If we take a point on the train,
V is having gradient, but the variation of V is straight line. Okay, I'll explain it. Everything is going here. So electric field is gradient of potential, right? It is negative gradient. Let me assume this is x-axis. Okay, here electric field is uniform. So this gradient is, so the variation of V versus x will be a straight line.
Yes, sir.
That's what is happening here. It's 5, 4.9 volts, and here it is 4.5 volts, and here it is 0 volts. But the rate at which it's varying, it's a straight line.
Sir, I'm asking points within that sheet will have different potential, no?
Yeah.
That's what I'm asking.
No. See, electric field is Ex I cap. There is no J component. So if you have to get potential in the y direction, if you have to get Ey, it will be gradient in the y direction. So if you have to get electric field in the y direction, I have to take the gradient of potential, but in the y direction. with respect to y. Here it is with respect to x. This will give me ex. To get ey, I have to get with respect to y. There is no variation with respect to y, the potential. Or the electric field in the y direction is 0 because it's along x. For it to be 0, this v should be uniform. V with respect to y should be a straight line. Constant. Slope is 0. That's what is happening here. The potential here, potential here, potential here, which is the same y, is constant. So with respect
So
to
can
this,
you mark one point outside the sheet with respect to which the potential is
no. Going outside will make it complicated. You have to stay well within where the electric field is uniform and it's in the x direction only.
okay? Thank you.
Outside will be complicated.
Yes,
So that's why when you study capacitance, you assume it's very, very close, and my point is inside. So it's as if I'm not bothering about these things. So it's as if the sheet is infinite because the difference between the distance between the plates will be very small.
okay.
So similarly, if you have positive charge and negative charge, the equipotential surfaces will look like this. It's actually a little bit difficult to visualize. How will you visualize? And if you have two positive charge, you look like this. Okay. Another thing is the electric field and the equipotential surface will make 90 degrees. The electric field lines and the equipotential surfaces this angle is 90 degrees. Okay, so if the electric field is like this, I have to draw my equipotential surface will be like this. So that at all the points where it's cutting this surface will be 90 degrees.
Here we should not take that area vector also.
No, area vector is area vector. Why do you want to take area vector? We just have to take this formula. Electric field is this one, gradient of potential. That will give me the direction of, this will imply the direction of electric field is perpendicular to the surface or it is parallel to the area vector. Okay,
So here that potential at y direction only constant, no sir, in this case, since that is along x-axis.
Yeah, potential is not constant in the y direction.
It is constant, no sir, by this formula, Ey equal to 0.
Yes, that's what is here. No?
But with respect to x-axis, potential varies, no sir.
Yes, this one.
Yes, sir.
Okay, and because it's only x gradient is there, it will give electric field in the x direction. There is no y gradient, so the electric field in the y direction is 0. And that is the starting point, right? The electric field they have given us only in the x. The electric field is only along x, so Ey is 0. So along y, potential is uniform, constant, or uniform.
Yes, sir.
Okay, so in general, this will be a picture. So the electric field lines will be like this, and the equipotential surface V, and the next will V plus delta V, and if the potential is decreasing, delta will be positive. If the potential is decreasing, it will be negative. So let me assume it's positive. So the electric field direction is like this. Along the direction of electric field, the potential will increase. Because fine. So these were equipotential surfaces. So to get the work, suppose I'm moving a point charge from A to B, where A is on this surface and P is on this surface. It's force into distance, that is E into delta L. That should be equal to the increase in the potential. work done in moving unit positive charge from A to B. Okay. So from this I get electric field as minus delta V by delta L. So that is gradient of potential. So previously I have not derived that formula. Here I am trying to derive that formula. Why electric field is gradient of potential. That you get from the work done in moving charge is increasing the potential. So potential of system of charges. So so far we have studied potential due to a system at a point due to a system of charges, but here I have two charges. So what is the work done in building this system? So initially I have only, so initially these two charges are kept at infinity. So I bring charge Q1 from infinity to this point. So what will be the work done for that? We should be knowing, right?
0.
Because there is no electric field initially. So electric field is not that I don't do any work. And the second charge I'm bringing now from Q2, but when I bring in the second charge, the charge Q1 is already present. So there will be electric field. So I have to do some work against electric field. So I can do the integration. I just have to say work done will be the change in potential from the initial point to the final point. So the potential of the final point, this one is KQ1 by R12. So that will be the work done. So work done bringing charge Q2 from infinity is Q2 into V2. Work done bringing me positive charge from infinity is the potential difference V. Bring a charge Q2, the work done is Q2 into the potential difference. And initial potential is 0 because at infinity. So work done is this one. So work done in assembling the system is K into Q1, Q2 by R12. Okay.
Yes, sir.
So if you have more than two charges, so say I'm bringing a third charge. Okay. So here also I can do the same argument. For the first charge, the work done is 0. To bring the second charge, the work done
Sir,
is
sir, in the above expression, why minus sign is not present here?
See,
Here also electric field and the direction opposite, no. So we have to put that minus sign.
yeah, see that is negative, and also it's F dot ds, no. So if the direction of F and ds are opposite, there will be a negative sign there.
Yes, sir.
So the electric field direction is outwards, okay, and this displacement is inwards. So that will give a cos 180. So that minus will cancel. Okay, if you get too much into maths, you might get confused and make mistakes. So just say whether work is done or work is, you have to do work, right?
Yes, sir.
So work done should be positive to bring a positive charge.
If I'm doing work means then it should decrease negative only, no, sir. Some of the energy will be lost.
Work done is F dot dr, no?
Yes, sir. And F and D are in opposite direction.
Which F? The F? No. See, the force that you are applying to overcome that repulsive force is inwards, no? The work is done by you. Okay, so the force applied by you is inwards.
And that and the R direction also. Okay. Okay,
So
same direction.
yeah, don't if it, that's what I'm saying. You have to think physically also, otherwise you'll get confused. So to bring a positive
Okay.
charge, you have to do work because you have to overcome the repulsive force. So work is done on the charge. Okay, so when you do work on the charge, the potential will increase. So the work done on the charge is the increase in potential energy. So initial potential is 0 minus the final potential energy. That will go to the work done. So potential of the system is increase in potential energy. That is K into Q1 by R. So similarly, if you have three charges, to bring the first charge, this is the work done. To bring the second charge, there will be potential due to both Q1 and Q2. So both Q1 and Q2 will give a potential at that this location, and that potential will be KQ2 by R23 and KQ1 by R31. That into Q3 will be the work done in bringing the charge 3 to this point. So this first term is bringing work done in bringing the charge Q2, and these two terms are work done in bringing the charge Q3. Okay. So the way to remember this formula is you have to take all the interactions. So when I have three charges, there will be 3 interactions, 1, 2, and 3, and each interaction will give a potential energy. So this interaction will give a potential energy of this one, and this interaction is this one, and this interaction will give a potential energy of this one. Similarly, if I have n charges, there will be n factorial lines. Actually, that will become more complicated. Okay, so whatever is the lines, one term will correspond to that line. Is it clear?
Yes, sir.
Suppose I have 4 charges. Q1, it need not be rectangle also, it can be any arbitrary shape. Q3 and Q4, and here there will be a lot of interactions. So there will be how many terms? This will give one term, and this is second term,
Subtraction.
third term, fifth term, and then sixth term. So the potential energy of the system will have 6 terms. There is no other interaction. Okay, for 3 charges, it is just 3.
Yes, sir.
So in addition to that, take some time. So any questions in this particular chapter or the
Tomorrow I will send you my doubts, sir. I didn't start. Sorry.
doubts or the problems?
Sorry, sir. What?
No, you have doubts or you have problems to solve?
I didn't solve today, sir, from this chapter.
No. Okay, tomorrow you are saying you will send. No, so you will send the problems you are not able to solve. You have some doubts. Doubt means some concept doubts.
Yes, sir.
Okay, so you have any doubts now?
Now, no, sir.
Okay. So if you want, you can note this link. Here there are some questions. Suppose you click electrostatics. Previous year questions are there. Okay, here may I do those problems. Okay, fine. Okay, some of the things you might be knowing. So you're giving practice test now, mock test.
But I didn't complete my syllabus lecture.
What? You're dropping, no? What do you mean you're not completed?
No, sir.
It's important that you have to take mock tests every week. Otherwise, it will be difficult. While studying in Akash, they would ask you to take mock test, no?
But during last 2 months of that,
Yeah. Right now we are the exam will be in June, no?
yes, sir, most probably. June or July, sir.
Why do you say July? Have the dates have come?
No, sir, they are postponing NEET PG and all. From that, the experts will have predictions now in YouTube
Okay,
and all.
but you should be ready for June because you don't know what will happen. And you have to take a test every week. And in the test, the total duration is 3 hours, no?
Yes, sir.
So which paper you solve first, biology or physics? Obviously biology.
Biology, sir.
And second is what?
Chemistry.
And third is physics, no? So how much time you have for physics? 1 hour or more than that?
1 hour, sir.
Actually, biology will not. What about chemistry? How much time does it take?
Sorry, sir, what?
No, chemistry portion in the test. How much time will it take to during the test?
1 hour, sir, but biology less than 1 hour only.
No, chemistry should also take less, no?
No, sir, I will take 1 hour, sir.
That is the problem.
Usually.
See, JE students, they do chemistry for half an hour and physics 1 hour and maths 1.5 hours. I'm not saying that is the always happening, but in general, I'm saying chemistry half an hour they will take, physics 1 hour, and maths they will take 1.5 hours. So since I think you should okay, I don't know, you should try to finish chemistry also faster. Biology will 1 hour because that's the main subject for you. Chemistry you should finish it faster and spend extra time on this physics. And number of questions have changed from previous year. Right now I think there are 43 questions, no?
No, totally 200 questions, sir. 5 questions,
No,
10 questions extra.
physics how many questions? 50.
Yes, sir.
And 50 questions same mark or different marks?
Same marks only, sir.
But it should come to 180, no?
They will give 50. Out of 50, we have to write only 45 questions, sir.
Okay, so
5
45.
choice.
So 45 into 5 is 180. 180 is it? Yeah. 90. No.
45 into 4, sir, only.
Okay, so
490.
okay, so 45 into 4, 190. Okay, so 45 questions is 1 hour. So it's almost like 1.5 minutes for a question. So unless you practice things, it will be difficult. Okay. Okay, suppose a charge of proton and electron differs slightly. One of them is minus E, the other one is E plus delta E. And what is the value of E?
1.6 into 10 power minus 19.
Plus or minus?
Minus for electron.
No. This is the basic mixture you're making. Always the symbol is plus only. The charge of electron is minus E. Okay.
Oh.
Always E is positive, but the charge of electron is minus E.
Okay.
Okay. Don't make that mistake. So this is the electron. So the positive proton is having an extra charge. So then let's start between the two hydrogen, place the distance T apart is 0. Then delta E is of the order of. So electrostatic force and gravitational force between two hydrogen atoms separated by distance D. So to try this problem, we have pen and paper. So first step is to draw a diagram. So he's saying two hydrogen atoms, right? What is a hydrogen atom? Hydrogen atom is One proton plus one electron.
Sir, with no neutron.
Okay, so what is, so in general this sum of this charge is how much? Zero, right?
Zero.
In normal situation, but here the sum won't be zero because electron and proton are not equal charges. So here the sum of charges is delta E. Is this clear?
Yes, sir.
So here I have one hydrogen atom and here I have another hydrogen atom. What is the charge of this hydrogen atom?
No charge.
No, that's in normal situation. But here,
Positive charge.
yeah, and it is delta E. This value. Okay,
Yes, sir.
so because of there will be a repulsive force, and the repulsive force is delta E square by distance square into K, and this is balanced by attractive force, and the attractive force is G into M square by D square. Is that correct? Yes, no?
Yes. Yes, sir.
So D square will go away. Okay, and K is 9 10 to 9, and G is how much?
6.10⁻⁻11.
Okay, so you give me delta E equal to G by K square root into N. So G is 6.67 into 10 raised to minus. Is this correct?
Yes, sir.
Is, so this is divided, no? So 9 into 10 raised to 9. So it is 10 raised to minus 20. So this will become 10 raised to minus 10, and 6/9 approximately, and mass is 1.6 into 10 raised to minus 27.
37.
10 raised to minus 37.
Second option.
56 is 2. So the thing is, you have to understand the question. Otherwise, if you don't understand the question, that will come if you keep practicing questions. Okay. So in general, the charge of this thing atom is neutral, but here is an imaginary situation in which the charge of the electron is negative, but the charge of the proton is E plus delta E, and E is a positive quantity. That you should know. That's a basic thing.
Yes, sir.
How many physics problems you are solving per day?
15, sir.
And their new problems are already solved problems.
New only, sir. I
How-
told you, no, sir. Last year I didn't solve. I barely solved the problems. I only revised the class note. That's it.
Okay, uniformly charged rod of length 4 centimeters and of linear charge density lambda is placed as shown in the figure. The exponent electric. This is very trivial, right? If you know the formula. Actually, this is not infinite rod. Calculate put at point P. So this is not actually NCRT. Okay, this is AIMS, right? This is not part of NCRT. NCRT,
Yes, sir.
NCRT have an infinite rod, but here is a finite length rod. So I think no, I think You can leave it because aims. Okay, this one we have just did it. Okay, this is a simple thing. This is a conceptual question. This you should be knowing. So just answer this one, 55. Read the question. The diagram shown below. You know what's equipotential, no? It's an equipotential
Yes, sir.
surface. Okay, 10 means all these points here are 10 volts. This point, all this point on the surface. So this is 30. So obviously this thing should be 20 because it's looking equal. And this is 10. Okay. A positive charge move from A to B in each diagram. A is here, B is here. Okay. In 4 cases, okay, the work done is seen. Is option A true? Option 1, 4 cases, the work done is seen. Work done is potential difference, right? So one is true or not?
Yes, sir. Potential.
So one is true, right?
Yes, sir.
What about 2? Minimum work is required. Okay. Same concept only. Minimum work is okay. These things are obviously not true because one is true. Okay, it's a trivial question. Okay, this is also trivial. This you know, right? What is the answer? What is the electric field here? Because of this plus sigma.
Sigma by 2 epsilon naught.
And the direction is this way, right?
Positive charge, sir.
Yeah. So this direction is correct or not?
Yes, sir.
Okay. What about the other one, 2 sigma? Because of 2 sigma, what is the electric field at this point? 2 sigma.
In between.
2 sigma by 2 epsilon not right?
Yes, sir.
Because of sigma, it is sigma by 2 epsilon naught. Because of 2 sigma, it will be 2 sigma by 2 epsilon naught. And the direction will be this way. Right?
Yes.
So the sum of
Yes,
these two is how much?
we have to minus it now, sir.
Yeah, because the directions are opposite.
Sigma by 2 epsilon naught.
$54 is 1. And what is the other one we saw here? 55 is also 1. 53 is also 1. Do you want this link? I can send it to you by WhatsApp.
Okay, sir.
Okay, here questions are there and also solutions are there. But please, you first try the question and then you can do it on your own. So just see whether you can copy this one. Can you just copy it now? Oh, you're using mobile, is it? Can you click on this link on your mobile? Okay, right. So just store this, save this, bookmark this one. Your laptop, what is happening to it?
Because I will still not prepared.
No, so when will it get repaired?
Okay.
No, the full monitor is damaged or what?
Sorry, sir, what?
No, laptop, the monitor is damaged or what? What is the problem?
Lip, display has been broken. So
Okay, that means you have to buy new laptop, no? Or you can change it.
I can change it, sir.
So okay, so when will it do it?
No, 1 minute. Pa,
Okay. Okay, son. We'll close now.
okay, sir. Thank
Okay.
you.
So laptop, will it get fixed or not?
You will get fixed, sir.
How much time? Because the thing is, notes are in JNT format. So for that, if you have to download that software, that will work only in the Windows system. And another thing is, are you looking at my notes or not? Because you have to remember, no, what I am saying, no. So unless you
Yes,
look at the notes, you won't be able to recollect.
yes, sir.
Okay, let's close now. Bye. Good night.
Bye, sir.